So far we have studied phase transformations, and even when we consider a simple phase transformation, for instance, suppose I am talking about solidification from the liquid state to the solid state. And now for now I will assume that there is a pure metal which is in the liquid state which is getting solidified. So the final solid typically consists of a polycrystalline microstructure. That means there are entities like grain boundaries, and within these grains themselves there are defects like dislocations present. That means that along with this phase transformation, I have a complete transformation of the microstructure, and we have already defined a microstructure as so along with this phase transformation, whereas the simplest one we can think of, a pure liquid going to a solid, we have complete change in microstructure. For instance, the solid phase forms, there are defects like grain boundaries and dislocations, and there are stress fields associated with these dislocations. That means that the entire all the components of the microstructure change when there is a phase transformation. But let us now consider certain other type of transformations wherein in true sense there is no change in the what you might call the phases, but it is the subtler aspects of microstructure which get transformed. So let us consider those kind of features in this, and we talk about three of them here. One is called recovery, other is recrystallization, and third is grain growth. Suppose we plastically deform a material, and we typically call this, when you do it under cold conditions, as cold work. Under such circumstances, typically the point defect density, typically vacancies etc. increases, and also the dislocation density increases. Now using at the end of these set of slides, we will try to understand that what is the correct definition of cold work. For now we will assume that it is a temperature regime, that means we are at a low temperature regime. Typically let us assume now that we are less than 0.3, let us mark out this, we are less than about 0.3 Tm, and we are doing working which is called cold working, and in the process we are increasing the defect density, which includes the point defect density and the dislocation density. So when I am doing cold working, the material becomes a store of energy and the strain energy in the material increases. Typically if you are spending say X amount of energy, about 1 to 10% of this energy expended is stored in the form of strain in the material, and this strain typically we have seen is via the increase in dislocation density and other defects within the material. Now that implies that suppose I have an well annealed material, which is of course well annealed polycrystalline material, like let me take copper or aluminum. The dislocation density is of the order of about 10 power 6 to 10 power 9, and when you do cold working of this material, not only does the material become stronger because of this cold work, but the dislocation density increases to about 10 power 12 to 10 power 14. In fact, it is the increase in dislocation density which is causing the increase in strength of the material. So there is a few orders of magnitude increase in dislocation density, and as you have seen, these the strain fields of these dislocations store energy, and about say for instance about 1/10 or about 1/100th of the energy expended in cold work is stored as strain energy within the material. Now when you anneal such a material, that means heat it to some temperature and hold it, the material tends to lose the stored energy and tries to come back to its original state. That means a state wherein the defect density is small, and that implies if I am doing cold work, I have an increase in defect density leading to an increase in strength of the material, and after annealing the material becomes softer and the dislocation density would decrease. This annealing itself can be done under two circumstances. That means we can do an annealing under slightly lower temperatures, or we can do it at higher temperatures. At lower temperatures, of course, we are supplying less amount of activation energy, and the processes which take place are collectively called recovery. And at higher temperatures, we have the phenomena of recrystallization, and we will try to understand these technical terms in little more detail in the coming slides. So, we have a cold work material which has been plastically deformed, for instance by like rolling, forging, extrusion, etc. And after the material has been cold worked, if you heat it to a certain high temperature and hold it, then there are two kinds of process taking place within the material depending on the temperature to which you heat. One, at low temperatures you have recovery, and at higher temperatures you have a phenomenon known as recrystallization. Now, therefore, during annealing you can, and if you give a sufficient kinetic energy, suppose you are holding at high temperatures, you would have recovery followed by recrystallization followed by grain growth. In the case of even high temperatures, there would be recovery, but then since the dominant process is recrystallization, we have written it as recrystallization. So, in the whole process, we will see that the physical properties of the material changes, and in fact physical and electrical properties etc. change, and in the process you would notice that the material is changing its properties due to a change in microstructure. And now, as we pointed out, there is actually no phase transformation involved in these processes, it is actually what you might call microstructural transformation. So, cold work leads to an increased strength, an increased hardness. It also leads to an increased electrical resistance because of the point defect density increase and dislocation density increase, but the ductility of the material comes down. And changes typically occur to all physical and mechanical properties, which are, we call it, structure dependent properties or the microstructure dependent properties. In X-ray diffraction, you will notice that Loewe patterns of single crystals show pronounced asterism. That means they look like star like and they are no longer well defined spots, and these are due to lattice curvatures. Debye-Scherrer photographs show line broadening, and in fact this line broadening can be used to characterize the strain in the material. That means we can compute the strain in the material by knowing the amount of line broadening. So, cold work changes many of the physical and mechanical properties, which include the strength, the hardness, the electrical resistance and ductility, and if you do annealing, the reverse, you can actually reverse and get back the material to its original well annealed state. Now, what does this term recovery mean? Recovery takes place at low temperatures of annealing, and if you look under an optical microscope and not under, for instance, an high transmission electron microscope, but in an optical microscope or even a scanning electron microscope, you would note that there is apparently no change in microstructure. And this is because what is happening is that the excess point defects created during cold work are absorbed at surfaces and grain boundaries, and also by dislocation climb. And as you know that it is not possible to observe vacancies or clusters of vacancies using optical or scanning electron microscope. Even in a transmission electron microscope, it is actually difficult to observe vacancies, and you have to use some indirect methods to find evidence for the presence of vacancies. Now, of course, certain vacancy clusters can be located in a transmission electron microscope. So, during recovery, there is a pronounced decrease in the excess point defect density, and for instance, vacancies which are created during cold working are absorbed at grain boundaries or surfaces, and even by dislocation climb, the vacancy concentration decreases. Now, additionally, one more thing happens to dislocations, that random dislocations of opposite sign come together and annihilate each other. Now, we will see a schematic of that in the next slide, and the dislocation tend to of the same sign arrange into low energy configuration. First thing, of course, that you have two kind of defects which we are talking about, which we discussed before when we talked about cold work. One is point defects, and typically the important one being vacancies, and the second one is dislocations. So, we have two kind of defects which are important, which have been altered during cold work, and when you are doing recovery, both these defects are affected, more so the vacancies and less the dislocations. But if you talk about defects, and now the pronounced effect is to the one, which is now my point defects, and of course this may include self interstitials. And if you are talking about dislocations, there is a lesser effect on dislocations. What happens is that dislocations of opposite sign come together and annihilate each other, that means they come towards each other, and finally you land up with a configuration in which you have a full atomic plane, that means no dislocation. Additionally, if you have dislocations of the same sign which are lying on different slip planes, then we will see as in the next micrograph that they can come together to form low energy configurations like low angle grain boundaries. So, we will come to this slide in a little more detail. So, but the important point to note is that though there is a small reduction in dislocation density and there are some low energy configurations which are arising during this recovery, but the overall reduction in dislocation density is small. So, this is an important point to note, and when these dislocations of same sign come together, for instance the schematic here, if they happen to be of edge character, then they can form tilt boundaries, and if they are of screw character, they can form twist boundaries. And when this process in which these low energy configurations of dislocations arise is called polygonization. So, let us try to understand this polygonization in the next slide. So, because of the presence of dislocations of course first we said that if the dislocations are of opposite sign, they can come together and annul each other. So, therefore, there is now only continuous planes and there are no dislocations. These are now atomic planes and there is no dislocation. Originally, for instance, we might have started off with a dislocation of one sign and a dislocation of another sign lying on the same slip plane. So, by this process they can annihilate each other, but suppose I am talking about dislocations of the same sign present in a certain axis, then you can see that so many dislocations of the same sign give actually bend the crystal. So, you have a bending of the crystal. So, there is a pronounced bending of the crystal. So, they have a bending of the crystal, though this bending is small, but presence of many dislocations can give a certain amount of bending to the crystal, and this bending of the crystal, as we noted before, we had noted here that this due to lattice curvatures, this can lead to effects on the Laue patterns if you take them, Laue diffraction patterns. Now, during recovery, of course, the thermal energy is not so high, so these dislocations cannot move over large distances, but they can come together in close vicinities. That means, say a few dislocations lying in this regime, they can all come together, which are all of course on a different slip plane. Say for instance, these three dislocations can all come together and form a low angle grain boundary. The important, of course, this phenomena overall is called polygonization, wherein originally there was a single crystal, a single bent crystal, as you can see here. So, this is my single bent crystal. This is now forming subcrystals. So, these are all now my subcrystals. So, this is subcrystal 1, then you may have of course subcrystal 2, and you can have a subcrystal 3 and a subcrystal 4. So, these original single crystal is now split into subcrystals, which are now between them has a low angle grain boundary. So, in this process which is called polygonization, an important phenomena which takes place is that these random dislocations, which are otherwise called statistically stored dislocations, become structural dislocations. We know that the role of statistically stored dislocations in plasticity is very different from those of structural dislocations, but in this process we see that random statistically stored dislocations by their motion and rearrangement become structural dislocations, and therefore now the material is split into subgrains and there are low angle grain boundaries between these subgrains. So, this is now my So, let me summarize what takes place during recovery. During recovery, a material partly goes down to a lower energy state, but because the thermal activation is not very large, we have not heated it to a very high temperature, the major reduction is actually in the point effect density, which could include self interstitials and vacancies, and these vacancies for instance could be absorbed at surface or grain boundaries, or dislocation climb can lead to, that means that suppose I had a dislocation here and there are some excess vacancies here. These vacancies can come and sit at the base, that means the atom can come here and fill up this space. So, in that process now my dislocation has gone up one level. So, this can be the climb process by which vacancy concentration will come down. Of course, the opposite will take place if a self interstitial diffuses to the core of the dislocation. And more importantly, we noted that though there is no observable change in an optical or a scanning electron micrograph, there could be rearrangements of dislocations etc., which can be seen in a transmission electron microscope, but the overall reduction in density of dislocations is only small. That means the material still has a reasonable dislocation density, and we may end up forming this polygonized subgrain structure. Now suppose I do my heat treatment at even higher temperatures, say for instance above, say for instance 0.3 Tm. So I can do my heat treatment above 0.3 Tm. So then there is a possibility that now I can refresh my entire microstructure. That means now we can have nucleation and growth of new strain free crystals, and this implies that the dislocation density and the vacancy or the point defect density in these new strain free crystals will be very small, and the material would have been restored to its original annealed state which was present before cold working started. So we can have nucleation and growth of strain free crystals. Sometimes nucleation of new grains in the usual sense may not be present, and grain boundary migration to regions of higher dislocation density may lead to the formation of strain free grains. So you can see in the schematic below, for instance, there is a grain boundary here, and one side of the grain boundary there is a region of low dislocation density. On the other side of the grain boundary there is region of higher dislocation density, and this grain boundary can sweep into this and we are assuming this now an high angle grain boundary sweeps into the region of higher dislocation density, and in the process the dislocations are absorbed at the grain boundary, and the overall dislocation density in the left hand side crystal also, or the left hand side grain also, decreases. So the region which was originally grain 1 will have a reduced dislocation density. Of course, we may have formation of new strain free crystals which may grow, which also leads to a reduced dislocation density. And of course, the driving force for this process is the fact that the free energy of the deformed crystal is higher than the free energy of the undeformed material, and therefore you have a free energy benefit when the material comes down to a low energy state. There is a temperature which is defined in this context, which is called the recrystallization temperature, because suppose I am using recrystallization as an intermediate step during, say for instance, some kind of a mechanical working process like forging, then I need to hold my material at certain temperature so that I have significant amount of softened material which can take further deformation without cracking. So temperature recrystallization unfortunately is a slightly notional term, which involves both percentages and time in its definition. So T recrystallization, or the temperature of recrystallization, is the temperature at which 50% of the material recrystallizes in 1 hour. That means that here the definition involves both percentages and time. We are not talking about, we are not waiting for infinity, we are not talking about instantaneous recrystallization of the entire material, but we are saying that 50% of the material, that means 50% of the stored energy needs to be reduced, and this needs to take place within an hour. So therefore, if I keep a material at the recrystallization temperature for 1 hour, then I can assume that 50% of my material will be recrystallized and it will be good enough to be cold worked again. Now, if this recrystallization or the working itself is done at a higher temperature, wherein recrystallization can take place actively during working, such a recrystallization would actually be called dynamic recrystallization. That means that I do not have to have a separate recrystallization step between the working steps. Therefore, I am doing my working at hot working, and again let me warn once more that these terms like hot working and cold working are technical terms, and we will be defining them in the coming slides. But the important point is that suppose I do my working at a high enough temperature that recrystallization is actively taking place while the deformation is in progress, that implies that I do not have to have a separate step wherein I have to recrystallize the material before I do further deformation. A few points about recrystallization temperature. So, once again, what is the definition of recrystallization temperature? It is the temperature at which 50% of material recrystallizes in 1 hour. If you increase the amount of deformation, the recrystallization temperature decreases. That means more the deformation I give, the lower the temperature I have to heat to form these strain free crystals. If my initial grain size decreases, the recrystallization temperature decreases. That means that if I have and also if you have high amount of cold work, that means higher amount of deformation along with low initial grain size, the finer will be the final recrystallized grains. Therefore, if I am interested in producing a fine crystallite size, then I need to start of course with a lower grain size and I have to do a high amount of cold work. And if the cold work temperature increases, then the lower amount of strain energy is stored in the material, because as I pointed out, some of these processes can actually of recovery etc. can take place while deformation is in progress, and therefore my recrystallization temperature increases because less amount of energy is stored. The rate of recrystallization is an exponential function of temperature. This is something like the Arrhenius behavior, but we have to note that at the heart of these recrystallization there are not one single process but multiple complex processes. Therefore, the activation energy which you calculate using this Arrhenius kind of function is not for a single process but for a complex set of processes. The recrystallization temperature is a strong function of the purity of the material. That means that suppose I take recrystallization temperature of, for instance, very pure materials of the order of 0.3 Tm, but suppose I take impure version of the same material, it is between 0.5 and 0.6 Tm. Like for example, if you take pure aluminum, which is about 99.999% aluminum, the recrystallization temperature is about 75 degrees Celsius. But suppose I take commercial purity aluminum, which may have other impurities, then the recrystallization temperature increases to about 275 degrees Celsius. The reason for this is that the impurity atoms, and all the impurity atoms need not always be equally soluble in the lattice or the grain boundary. Many of them may not have poor solubility in the in aluminum for instance, or the lattice, and therefore they typically tend to segregate at grain boundaries, and these typically retard the motion of the grain boundary itself, which is called solute drag, and this can be used to retain the strength of materials at high temperatures. So, what we are talking about here, suppose I had a pure material whose grain boundary, now this is my polycrystalline material, and therefore there are grain boundaries, and this grain boundary is pure. On the other hand, in a material of lower purity, you would find that at least there are some elements which tend to segregate at grain boundaries. Now, if this grain boundary has to move, this implies, suppose I have my grain boundary and there are solute atoms which have segregated to this grain boundary. If this grain boundary moves out, this implies that the solute atoms would be left inside the grain. This is an energetically unfavorable situation because these elements are typically not very soluble in the lattice. Therefore, what would happen is that these elements have to diffuse along with the grain boundary so that they can remain segregated at the grain boundary, and this whole process, that means coupled process, is less free as compared to just the motion of the grain boundary. So, these grain boundaries can move easily, these grain boundaries with segregations cannot move that easily, and therefore, these grain boundaries feel what you call a solute drag, and in the process the recrystallization is difficult in such materials, and this solute drag can be used to retain the strength of materials at high temperature. That means you do not have recrystallization taking place readily. That means the energy as put in as cold work, the stronger material remains strong even at higher temperatures. So, as I pointed out, let me repeat this. The impurity atoms segregate to the grain boundary and retard their motion. This process of solute drag can be used to retain the strength of materials at high temperatures. Apart from of course solute atoms, you may also have second phase particles or precipitates which sit at grain boundary, which also may actually retard the motion of grain boundaries. So, let us try to understand, summarize this slide, that what are the factors which affect recrystallization. We are worried about the amount of deformation or the recrystallization temperature in particular. So, we are worried about the amount of deformation I have caused to the material. What temperature did I cause this deformation? In other words, how much of this energy I input actually is stored in the microstructure in the form of defects. and we have noted the higher the deformation or higher the energy stored, lower will be the recrystallization temperature. Additionally, we have noted that it is a function of the purity of the material. So, we have to worry about the amount of deformation we put in, the purity of the material, the lesser the purity, higher will be the recrystallization temperature, as nicely demonstrated for the case of aluminum, where the recrystallization temperature can drastically increase if you take an impure material. Further, we also have to worry about the grain size of the starting material which was deformed. Additionally, we had also noted that the rate of recrystallization is an exponential function of temperature, and it looks like an Arrhenius equation, but then this activation energy, as we should note, is a representative of very many complex processes taking place and should not be interpreted in a simple term as if it were a single as if recrystallization were a single fundamental process. Now, we are right in a position to define what is cold work, what is hot work, or what is cold working and what is hot working, and further what we can call as warm working. So, if you, because now we have a correct definition, correct platform to define these terms, if you do plastic deformation above the recrystallization temperature, this is called hot working, and that implies that the material can spontaneously recrystallize as the deformation is taking place, and this implies also that the material constantly remains soft and its ductility is not lost while working is taking place. On the other hand, suppose you do plastic deformation below the recrystallization temperature, it is called cold work, and this range can further be subdivided into 3 regimes, as suppose I do, for instance, typically recrystallization above 0.6 Tm, I can call this hot working. If I do it in the low temperature regime below 0.3 Tm, so this is my regime, then I call it cold working, wherein typically my material becomes a battery of energy, the defect density increases. That means that in the cold working regime, the effect of strain hardening are not negated, recovery mechanisms involve mainly motion of point defects, and my material tends to accumulate these defects and its ductility would reduce, but its strength would increase. When a material is hot worked, on the other hand, above this 0.6 Tm, this regime, so I am in this high temperature regime, then the sample remains soft and ductile. The effect of strain hardening are negated by dynamic and static processes which keep the material ductile. That means there are processes taking place while my deformation is happening. The lower limit of hot working is typically taken as 0.6 Tm. The temperature regime between the two, which is now between 0.6 and 0.3 Tm, is often called warm working, wherein of course there is some amount of recovery and some amount of recrystallization taking place, but it is a regime between hot working and cold working. So, if a person wants to increase the strength of the material, he would do cold working. On the other hand, he wants to maintain the give extended deformation of the material without any intermediate processing steps like recrystallization, he would actually do hot working of the material. So, somewhere around between the two is typically quoted as the recrystallization temperature, which is about 0.4 Tm. Finally, even in a recrystallized material, there is of course, the recrystallized material is in a lower energy state as compared to the cold work material, because now my dislocation density is smaller, my point defect density is smaller. Still, we have energy stored in the form of grain boundaries, which means there is interfacial energy in the form of grain boundaries, and this energy the crystal can lower by causing a phenomena known as grain growth. In grain growth, what we are noticing is that typically grain growth implies, of course, all the grains cannot grow. What it implies is that the larger grains grow at the expense of smaller grains, so that my overall grain size decreases. So, let me show this schematically on the board. So, initially we have say for instance a fine grained material, which could be of course recrystallized material. So, I have my grain structure, and after grain growth I would notice typically that my grain size would have increased. So, for instance, there were so many grains in this place, 1, 2, 3, 4, 5, 6, and I have only 2 grains in this place. So, grain growth implies that my average grain size increases. That means the grain boundary area per unit volume decreases. the grain size increases, number 1. So, what is the driving force for this? The driving force for the fact that the grain boundary area per unit volume in a fine grain structure is more as compared to this. That means during grain growth, my grain boundary area per unit volume decreases, which means my energy associated with the grain boundaries decreases. This is happening by an increase in grain size. Of course, grain size increase does not mean that each one of these grains is increasing. There, of course, for instance, in a structure like this, there could be small grains like 7. This small grain may vanish, and this will typically happen at the expense of the larger grain. That means the smaller grains vanish at the expense of the larger grains. So, two important things I have to note. Overall, there is a reduction in interfacial energy as I grow from a fine grain material to a coarse grain material. Because of my increase in grain size, of course, further my strength decreases as compared even to a, what you might call a recrystallized state, because of that the grain size goes into Hall-Petch relationship for the determination of strength. That means my yield strength would decrease from when I go from here to here. That means even though I do not have a very high dislocation density, or the dislocation density does not change much when I go from a fine grain to a coarse grain during grain growth, what happens typically is that my overall strength can drop because of the Hall-Petch effect. Now, what drives this process globally is very clear. It is a reduction in the grain boundary energy. So, globally it is actually a reduction in grain boundary energy which drives this process. But for every process to take place, we have to worry about two criteria. One is known as the global criteria, which is typically a thermodynamic criteria, but additionally we also have to about a local criteria, which sometimes may behave like a stress or a stress intensity, or even like a local energy density criteria. To give an example, for instance, suppose I am having a material with a crack in it. Suppose I have a body, a large body in which I have a crack, and I cause the deformation of this body, stretch it a little bit and hold it. Then the strain energy stored in the material can drive the crack growth, but the global I globally can understand, suppose this crack grows from this length to a longer length. So, my original length is A0 and it grows to a longer length A1. Then the strain energy is relieved, and the strain energy now goes into goes to the formation of the part of it goes to the formation of the interfacial energy or the broken bonds, and the overall strain energy of the material comes down. But suppose for this crack growth to take place, I know that my strain energy drives this whole process. But on the other hand, if suppose I take a circular crack vis-a-vis a sharp crack like this, it is clear that the stress concentration which needs to cause breaking of bonds is lower in the case of a circular crack as compared to a sharp crack. That means here I would expect better chance of my crack growth to take place. That means even though the overall energy stored in the body may be large here, crack growth will not take place because locally it is not satisfying the fact that enough energy density or enough stress is not available at the tip of the crack to break the bonds. So, therefore, even as in the case of this crack growth problem, we also have to worry about not only about the global criteria, also about a local criteria, and locally it is bond maximization or what you might call coordination number maximization which drives my grain growth. So, for instance, to take this schematic, for instance, there is a grain boundary here, and this grain boundary separates two grains which I can call grain 1 and grain 2. If you look at because of the curvature of this grain boundary, you can note that the atom sitting on the right hand side, right hand grain 2, is actually bonded to 4 atoms. On the other hand, the atom sitting on the left hand side is only bonded to 3 atoms. That means the energy of the atom on the right hand side is lower, it has lowered its energy more as compared to the atom on the grain 1, the grey colored atoms. Of course, here we have to note that the 2 atoms, these are just been colored differently, but they are actually the same atom shown in 2 different grains. then what can happen is that suppose this atom jumps from grain 1 to grain 2 as shown schematically here. Of course, it has to jump over a small barrier, but this jump can take this atom from grain 1 to, and then it becomes part of grain 2. In the process, its coordination number has increased from 3 to 4. That means locally the energy of the system is going down when the grain boundary or the atomic jump takes place. This atomic jump automatically means that now my boundary, which was originally my green line, has now become a new boundary has formed here, and the overall process can take place in such a way that the grain boundary can migrate from right to left, causing more and more, when of course this will happen when more and more atoms jump from the right direction to the left direction, becoming part of the grain 2, and in the process the grain boundary sweeps from right to left, and overall this will lead to this grain on the left shrinking and the grain on the right of course growing. And as you can note that suppose I had two grains, of course I am not showing them, I am showing them very schematically here, that there is a smaller grain vis-a-vis a larger grain. You can note of course that the larger grain has a lower grain boundary curvature, and a smaller grain with a lower radius of curvature has a higher curvature, and therefore such a grain would tend to shrink, the smaller grain would tend to shrink and the larger grain would tend to grow, and in the process my overall number of grains would decrease. That means the grain energy, grain boundary interfacial area per unit volume would decrease. So we have seen that this grain growth is not driven only by the global criteria, but also by the local criteria, and the local criteria involves jump of atoms from which are poorly bonded to neighboring grains where there can be better bonded. That means the system energy can come down, and in the process the grain boundaries tends to move in such a way that the smaller grains tend to shrink and the larger grains tend to grow, and in other words the boundary moves towards its center of curvature, causing these what you might call smaller grains to vanish and larger grains to grow, and the overall number of grains hence comes down during grain growth. So we have seen that during process like recovery, recrystallization and grain growth, what we can now call them as microstructural transformations. That means there is no change in phases, but there is an active change in the microstructure, and we already know that microstructure can directly be associated with properties, and therefore let us now track how the properties change when this microstructure changes. We have noted that during recovery, of course the major change is to the point defect density. There is a small change of course in terms of the dislocation density and the rearrangement, but the major change is to the point defect density. During recrystallization, we have noted that there is a large change to the dislocation density, there are new strain free grains which may form, and that means that overall my entire microstructure is somehow refreshed. During grain growth, these strain free grains continue to grow, that means the overall grain size increases, and this further can lead to the change in the properties. So let us see how some of these properties, and here we are talking about properties like electrical conductivity, ductility and tensile strength, and all these of course are a function of the internal stress. The internal stress being in the form of these dislocation density, etc. Now what happens during cold work? So I have this process till this line here, which I can call the cold work regime. So what happens to these three properties in the cold work regime? You can see clearly that the electrical conductivity, which is shown in red, seriously is hampered by the increase in this point defect density. So what is happening during cold work? Of course also because of dislocation density. So what is happening is that the electrons which were moving unimpeded, who had a larger mean free path, they are now scattered because of this presence of these defects which distort the lattice, and there is a decrease in electrical conductivity. And the ductility also decreases during cold working, and of course the benefit we get is in terms of the tensile strength. That means my strength increases, but my ductility comes down, and this is what happens during cold work. And of course because now my overall strength is coming from one of the important factors being dislocation density, the internal stress also increases. So now I have a cold work state where my electrical conductivity is low here, my tensile strength is high, but my overall ductility is low. That means now if I further try to deform this material, it will not give you sufficient ductility. Now if such a material is held at a temperature so that I just caused recovery, then what happens is that you can see that some of the properties are severely affected. Like for instance, now there is a serious increase in my electrical conductivity. The ductility tends to recover a little bit, my internal stress also falls down a little bit, but not totally, but my tensile strength is still not changed much because I have an overall high amount of dislocation density. If I further hold the material cause at a higher temperature to cause recrystallization, during recrystallization of course what happens is that my tensile strength also comes down. Since my already I have my electrical conductivity has reached a sufficiently high value, it will tend to recover a little more because of the fact that now my dislocation density is coming down, but there is no pronounced change during recrystallization process. But the important change takes place to tensile strength, which seriously falls down, and therefore if I cause recrystallization of the material, my material from strong becomes weak. So I have this arrow along which it goes, and therefore now my recrystallized material is weak, that means my tensile strength decreases. Of course, it does not fall down to the lowest value possible, and this actually tends to happen only during grain growth. During grain growth further there is a decrease in the tensile strength, and therefore my material tends to lose its strength. My ductility already has come to its original near maximum value. You get a little more benefit, but not much. But the most important or actually sometimes ductility may even come down because of the increase in grain size, but here we note that the important change is to the tensile strength, which continues to fall if my grain size increases. This is due to the Hall-Petch effect. So we see here in this slide, which I summarize now, that when I try to take my cold work material with a high defect density and hold it at temperature so that I can process technical terms being used are recovery, recrystallization and grain growth. At each one of these stages, some of the properties tend to come back to its original state. So during cold work, for instance, the electrical conductivity comes down and the ductility comes down while the strength increases, and during most of the strength continues to remain even though I have caused a recovery process. The maximum fall in strength actually takes place during recrystallization process, and further the strength continues to drop when I cause my grain growth. The electrical conductivity actually recovers to most of its peak value during the recovery itself. That means that I do not have to wait for recrystallization, and this is because of the annihilation of point defects mostly, and therefore my lattice is less strained and I have a good amount of electrical conductivity. So microstructural transformations also lead to change in properties apart from phase transformation, which you have already seen that I can cause change in properties by phase transformations. Therefore, we have noted that if one is interested in engineering components, he can control the composition, but further he can engineer the microstructure to cause changes in properties, and for engineering the microstructure he may use various thermomechanical treatments which may include hot working, which may include quenching and tempering, etc. So you can use various thermal or thermomechanical treatments to engineer the microstructure, and the final microstructure should be such that it can serve the component well in the long term use. So this is the essential message of understanding that we should have a good understanding of the crystal structures, but further we should have a good understanding of the microstructure which comes from these crystal structure, so that I can understand the properties which come out of such a microstructure. So if one wants to learn material science, the four fundamental pillars of this are the physical structure, the electromagnetic structure, thermodynamics and kinetics. So this course tends to cover one of these four fundamental pillars, which is the physical structure, and therefore we have tried to include various length scales of this problem. So we have gone from point defects to dislocations to entire components to understand how I can engineer my physical structure, which can therefore give a handle on my properties.